Welcome back. So we were talking about contextually constrained deep learning, where by that term I mean learning scenarios where, in addition to having a performance-centric mindset, we want to make sure that some other context is also satisfied, or some other constraint is also satisfied. And we started this module by talking about privacy. And today we're going to talk about the memorization phenomenon in deep learning. And the reason I'm going to talk about this is that in some sense, and hopefully it's also intuitive, to think about the connection between privacy and memorization. And also, as we're going to see, both can be captured by looking at them through the lens of sensitivity. Okay, so we saw that in the context of differential privacy. And our hope today is to convey this the importance of this notion of sensitivity in the context of memorization as well. So let's get started then. So in terms of the motivation, so let's recall what we talked about in terms of privacy and differential privacy. So what we said basically was that we want to learn something useful about the population while not memorizing or learning something specific about an individual agent or an individual data point, okay? And we basically saw that our mechanism to achieve this is noise injection, okay? And the main idea was that by injecting noise, we can reduce the sensitivity of our model or our learning algorithm to individual data points. Therefore, we can ensure that certain level of privacy is ensured, okay? And this actually I think leads to this question, right? So we say that by privacy or differential privacy, we mean that our goal is to learn something useful about the population while not memorizing individual sample. So is it even possible to do this in all cases, okay? And I think that the answer basically is that it depends. It depends on the type of the data distribution, right? So if our data distribution is nice and let's say centered around some mean, okay, so basically it's to say that every data point is more or less the same, then we can kind of expect this to be feasible, okay? So meaning that not everyone is essential. So if I just introduce some level of noise, I'll be able to reduce the sensitivity of the model and still learn something useful about the entire population, not specific data points. On the other hand, and this kind of distribution is something that I will refer to it as non-long tail distribution, okay? On the other hand, if the data is long-tailed, then that's a different story. So what do I mean by long-tail data? Well, by that I mean that there are many small frequency events that occur with relatively low probability, okay? So essentially, the probability mass is not concentrated around the mean, but the majority of the mass is actually contributed by many small probability events, okay? And this is actually a phenomenon that we observe in practice. Lots of data distributions, lots of data sets that are standard and we use them to train our deep learning models in practice can be shown to follow a long-tailed data distribution, okay? And here I'm sort of visualizing this from one of the papers in the literature, and basically what this is showing is let's say the number of occurrence versus the type of the data or the populations or the classes, things like that. And as you can see here, this tail is actually very long, and a lot of the probability mass is actually captured by samples in the long tail of the data distribution. So why this may not be possible, therefore, to achieve, why we may not be able to learn something useful about the population without memorizing individual samples. So the idea is that if I want to be able to generalize to a specific subpopulation with a low frequency, intuitively, I have to memorize it. Otherwise, if I inject noise, given that I don't have enough instances of this subpopulation in my training data, noise is going to dominate. So I'm not going to learn anything useful about that subpopulation. On average, over the entire data, I'm going to perform well while maintaining the privacy. But if I put my emphasis on a specific type of data, I'm not going to do very well on those. Okay? So we kind of therefore need to memorize, and that's the message I'm going to basically talk about in this lecture, is that we have to kind of memorize these data points with low frequency in order to ensure that the generalization of our model is above some acceptable threshold. Okay? All right. So therefore, let's talk a little bit more mathematically about this long tail distribution. Again, what I'm showing here. Basically, a distribution is long tail where a large portion of the total probability mass is concentrated in the tail, okay, as opposed to around the mean, okay? Which basically means that, as I mentioned, there are many small frequency events or values that occur with a relatively low probability, okay? And the tail of this distribution basically extends far out. So mathematically, one way to talk about this is through the Zipf's law. And this is basically a law that I believe is originated from the natural language processing literature, talking about the frequency of the, let's say, the language words, right? So English words frequencies turns out to follow the Zipf's law, for instance, okay? So mathematically, the probability density is something that is proportional to, let's say, 1 over x to some power s, okay? So s could be 1, 2, 3, etc., okay? So this is basically one way to talk about long tail distributions that follow a version of Zipf's law, okay? We should sort of compare this with nice light tail distributions such as Gaussian, where the density is proportional to the exponential of minus x squared. What does this mean? It means that when x becomes large, basically when we are in the tail, the probability is very, very small, okay? So it decreases exponentially with x squared. So that's why we call it light tail. On the other hand, in the first case, although the probability is decreasing, but it doesn't decrease as fast as the Gaussian case, okay? So in the light tail, the distribution case, such as Gaussian, tail drops much more quickly, such that beyond a certain point, the probability of observing values far from the mean becomes extremely small. And this is not the case with the long tail distribution. All right. So what's the implication for learning? In particular, what do we mean by long tail samples? What kind of samples are long tail? So long tail data points in our training data are the atypical samples. So they are not like typical, they're not easy, right? So and they belong to subpopulations of, let's say, size order of 1 over n. So if n is the total number of data points that I have in my data, my data set, the samples that are long tail are the atypical one, which means that they belong to certain subclasses, subpopulations, where the frequency is very, very low. I only observe, let's say, for instance, an example of this could be the class of all cats, okay? So maybe I have a lot of images from all cats that are white color cats, okay? So that's one subpopulation, but another subpopulation could be black cats, okay? And I may not have enough samples from the black cats, okay? So therefore, we would call the black cats the long tail data points or atypical ones. On the other hand, the white cats in this example will be the typical data points, okay? Now, intuitively then, if the model hopes to learn these subpopulations that are atypical, meaning that if I want to make sure that my model not only generalizes, let's say, not only is able to identify and, let's say, categorize white cats, but also do so for black cats, intuitively it has to memorize these samples. There is no other way around it, okay? Now, two questions I would say arise here. So first of all, what do we mean by memorization exactly? Okay, mathematically, what's the definition of memorization? And secondly, when we say atypical examples, right? So are all atypical examples in our training data useful? So do I even need to care about the fact that I have to generalize to all atypical examples in my training data? Or maybe some are useless, okay? And here I'm going to answer the first question, the second question first. And the answer is no. So it turns out that atypical examples could include both hard examples, truly atypical ones that we need them to make sure we generalize over all subpopulations in our training data, as well as noisy samples. Okay? So noisy, by that I mean, it could mean mislabeled. So for instance, I could have like image of a cat and I label it as dog. Outliers, duplicated samples, so meaning that an image appeared with two different labels in our training data, etc. Okay, and naturally, when we have a noisy example, that's not necessarily a useful one. So it may be fine not to generalize to noisy examples in our training data, because it could be unlikely to observe them at test time or at inference. On the other hand, the truly hard atypical examples are those that we need to basically memorize to make sure we generalize to them at inference. And this figure is kind of demonstrating this idea that, again, if this is taken from a paper in the literature that sort of shows the frequency of examples across different classes in a typical data set. And here there could be, for each class or each subpopulation, you can have both clean data. So for instance, this image of a cat, which is a clean data, as well as mislabeled data, where, for instance, you can have image of a dog or a truck that is labeled as cat. Okay? And this labeling is happened by mistake, let's say, when we were putting together the training data. Okay? All right. So that's the answer to the second question, that no, all atypical examples are not necessary. Now let's talk about the are not necessary to basically to be memorized and generalized too. But now let's talk about the other question, which was basically the mathematical definition of memorization. Okay, so intuitively, memorization means that model needs to rely on a specific training examples for inference, rather than learning general patterns applicable to unseen data. Okay, so specifically it means that I have to completely memorize this image and its label to make sure that I generalize to all other images that come from the same subpopulation. Okay. This intuitive definition leads to this elegant definition that is recently proposed in the literature. So let's assume that we have a randomized algorithm, a randomized learning algorithm, for instance, a stochastic gradient descent and its variations, okay? That we apply to a training data set S. So this could be, for instance, ImageNet, C410, C400, all of these data sets that we typically use to test and verify the efficacy of our deep learning models. So we have this randomized algorithm, a training data S, and we use this to learn some model. So HWS. And so this basically means that I have a hypothesis, a model, certain deep learning architecture, such as ResNet, which is parameterized by W. So W collects, for instance, the weights of different layers, and it is trained on model S. Okay? Then we can define the memorization score for each data point, okay, as follows. So the memorization score of, let's say, data point Zi, when I use the randomized algorithm A to train a model on training data S, is defined as the difference of basically these two probabilities. The first term is the probability of making a correct classification when this specific image was part of the training data. Okay, so as noted in this subscript, minus the probability of correct classification when I exclude this specific sample from the training data. Okay, so if the difference is near zero or exactly zero, that means that I'm not memorizing sample I in the training data. With or without this sample in my training data, I'm still able to correctly classify the sample. On the other hand, when this difference is, let's say, near 1, what that means is that I'm going to memorize sample 1. So there's a huge difference when I include sample I in my training data or not. When I include it, I'm able to correctly classify it, correctly predict its label. But when I exclude it from the training data, I'm going to make a mistake. Okay? So therefore, this is a very natural and meaningful definition of memorization phenomenon that basically is talking about what will happen in terms of correct classification of a specific sample when we include in the data versus when we exclude it from the data. Okay? So this is basically, the next point is sort of related to our main message, that this in some sense measures the sensitivity of the model's prediction to the removal of individual data points from the training set. Okay, so therefore, if my model, so you could make the following statement, that if the model is not sensitive to a specific data point, it's not going to memorize it. On the other hand, if the model is sensitive with respect to existence of a data point, it's going to memorize it. Okay? So therefore, there is an association between memorization and notion of sensitivity in this sense. Okay. So therefore, if again, what the definition says that if removing a single sample significantly alters the model's prediction for that data point, the model is going to memorize it. On the other hand, if the performance doesn't change much or remains kind of unchanged, it is considered stable, and basically the performance of the model on predicting the label does not rely on memorization. Rather, it relies on learning meaningful generalizable patterns. Okay, so let's try to visualize samples from a specific subpopulation, a specific class with varied memorization scores. Okay, so in particular, it should be sort of intuitive and clear by now that if the memorization score is low, sample is a typical sample. It's an easy sample. On the other hand, when the memorization score is near 1, the sample is a long tail sample. It belongs to a subpopulation with a very small frequency. Okay, so in some sense it could be again an atypical sample, something that is either hard for the model or something that contains noise. Okay, so this is taken from again one of the pioneering works in this area. That they sort of define the memorization score and visualize that for different images of bobsled in the ImageNet dataset. So here on this row we have samples where the memorization score for them is near 0. So that means that without them in the training data, we'll be able to predict their labels correctly. Okay. And as you can see here, these are kind of very nice, easy images of bobsled. It's quite visually clear from these images that we are talking about basically a bobsled. On the other hand, as we increase the memorization score, for instance, here the memorization score is 0.5, here is 0.1, we can sort of see that the images get harder and harder and less clear. For instance, in this row, the last row where the memorization score is 1, we have very difficult images. For instance, the first image is, I think, a bird's eye view of basically the bobsled. It's kind of difficult. And also we have some mistakes, some noisy samples. For instance, this is not necessarily like a bobsled, it's a snowmobile. A bobsled is non-motorized, snowmobile is motorized. This I'm not even sure what that is. Maybe it could be, I don't know, kind of a fish. And these two are also not images of bobsled. Okay? So therefore, when the memorization score is large, we could have very hard examples, okay, that we kind of need them if we want to hope to generalize to them later on in the inference. Or it could be that we have noisy samples. So ideally, we want to identify them and get rid of them before even training our model. Okay? So it is pointless to be able to generalize to this example, for instance. Okay? All right. So now let's try to formalize this notion. Okay? That we kind of need memorization to happen in order to make sure that our generalization performance is good, not only on typical examples, but also on atypical examples. Okay? So to that, I'm going to state this theorem, which is a simplified result from again one of the pioneering works in this area. So let E here denote the expected generalization error of our model HW, which is basically trained by our randomized algorithm A, for instance SGD, for a long tail data distribution PL. So basically here we are making an assumption that the distribution is long tailed. For instance, something that follows the Zipf's law. So that means that PL cannot be, for instance, something that's like a Gaussian distribution. Okay? So we have this distribution assumption, and for that we define the expected generalization error. Okay? Let's also consider the best achievable generalization error by any randomized algorithm. So here, crucially, we are fixing the distribution. So we assume that the distribution is still long tail. We assume that we have the same kind of a neural network architecture, same resonating, but we could change the learning algorithm. Okay. Let's define another error term. So E sub S denotes, E sub S of A and 1 denotes the number of examples that appear exactly once in the training data, meaning that their frequency is equal to 1. Okay? And not only the frequency is 1, but also they are mislabeled by our classifier. So classifier has made a mistake on them. Okay? Then we have this result that the generalization error is lower bounded by 2 terms. Naturally, it is lower bounded by the best generalization error that we can achieve. But there is this other term, which is some constant, let's say, that depends on the nature of our distribution and the number of examples that appeared once. Basically, they are atypical, and the model has mislabeled them. So what this is saying is that if we don't memorize these low frequency samples, and again, by memorization I mean that if we don't memorize the labels, the generalization error is not going to be optimal. Okay? So if we hope to reduce the gap between the expected generalization error and the best we can achieve, we kind of have to memorize these low frequency samples. So therefore, we have to make sure that our model does not mislabel these low frequency samples. Okay, so how does this relate to memorization? Crucially, you can show that the number of examples that appear once and are mislabeled by your model is actually the inverse additive of the memorization error. So there is this term here. So basically, the probability of misclassification when the sample is excluded from the training data, and the memorization score associated with that low frequency sample. Okay, so therefore, when the memorization score is 0, meaning that our model has not memorized this, this number is going to go up. Okay, and that means that the generalization given the equation number 3, the generalization error is going to be large. On the other hand, when the memorization score is near 1, meaning that our model has memorized this specific sample that appears once, then this is going to go down. So basically, we're going to memorize them, and then we're not going to make as many mistakes. So therefore, the generalization error is going to go down. Okay. So again, theory implies that to achieve the best performance, we kind of have to memorize these atypical examples to again make sure that we are not making as much mistakes on them, and therefore, due to this equation number 3, we can achieve the best generalization. All right. So let's try to also visualize the impact of the memorization score. And what the authors did is something very interesting. So they sort of try to remove samples with varied memorization score from the training data and see the impact on the inference, on the test error, okay? Or in this case, the test accuracy. And to emphasize the role of memorization, they compare this with random removal as well. Okay. So here, again, we have the results for 2 datasets, ImageNet and C400. The results are more or less the same. So let's focus on the ImageNet results. So we have 2 curves. The orange one is indicating when we remove samples from the training data based on their memorization score. And the green curve basically depends on so it demonstrates the random removal. Okay. And different points here indicate different fraction of data points being removed from the training data. Okay. All right. So basically, for instance, when I'm at this point, this means that I have removed all samples with memorization scores exceeding 0.8 from the training data. Okay. All right. So basically, what this result is showing is that when we remove samples with high memorization score beyond a set threshold, there is a significant drop in the model's performance compared to random dropout, random removal, as we can see here. Okay, and the gap sort of shrinks as we sort of remove samples with lower memorization score. Okay. There is also another observation we can make from this figure, and that's basically the fact that the data has long tail nature. Okay, so in particular, more than 50% of the samples, as we can see here, more than 50% of the samples have a memorization score below 0.1. So therefore, this result and this theorem suggests that memorization is kind of essential if we want to make sure that we have a low generalization error. Okay, and in the next part of this lecture, we're going to sort of try to connect memorization scores to differential privacy, given that naturally both of them are kind of trying to characterize the sensitivity of our model with respect to data. And then we're going to leverage this idea of sensitivity to talk about different memorization practices that could potentially help us to distinguish samples that need to be memorized because they are hard from samples that are memorized because they are noisy. I'll see you in the next part of the video.